A visionary gravitational wave mission, the Big Bang Observatory, not be confused with the Big Bear Observatory. I've told you before, Bill played a seminal role in getting LISA off the ground and is now in charge of the LISA test mission from the American side. But he and Sterl Finney are the two people who have done by far the most thinking about follow-on missions to LISA, and so that's what Bill's going to talk about for somewhere between 15 minutes and half an hour. And then the rest of the time will be Mark Kamiankowski on another topic.
Hopefully Mark will show up.
I told Mark that you begin about 1:30, so.
Okay, well that will turn out about right. So actually Sterl Finney is the one who's done most of the thinking about this future mission, not me, but we've worked a little bit together on trying to do the spacecraft configuration and the instrument capability and things like that. So I'll do my best to fill in for him. And so what Sterl has decided, and in fact the NASA committee has agreed with him, is that the main thing that you'd want with a future gravitational mission beyond LISA is to look for a stochastic background of gravitational waves from the early universe, from the Big Bang, from the cosmic inflation, maybe from some recombination or a phase transition of the electroweak and the strong forces separating. But the inflationary limit is the one that's best understood, perhaps, and so that's sort of sets the goal then for what you'd want a future mission to do. And so people talk about, in terms of frequency, the gravitational wave energy density of the universe compared to the energy density that would cause closure, if I'm saying this right. And so you expect a fraction of the energy density of the universe in terms of gravitational waves from inflation to be at most a part in 10 to the 15th of the closure density.
That's in a bandwidth equal to frequency.
That's right. So, the energy density per unit bandwidth, per bandwidth of 10 to the minus 2 hertz would have that energy density of 10 to the minus 15. Okay, so it's a very, very small signal. And plotted this way, it's flat as a function of frequency, whereas the gravitational wave sensitivities, this is not in strain amplitude age, but this shows the relative sensitivity of detectors. So I'm not interpreting this plot very well, but this line is sort of what the standard slow roll inflation curve would look like, which is well below the sensitivity of LISA or LIGO or pulsar timing.
The LIGO there is LIGO 1.
Okay, well LIGO 2 will be on the next plot. Pulsar timing might get quite a bit better. This signal is relatively stronger at lower frequencies. That's one thing. The other thing to point out about this curve, this is just some nominal slow roll inflation model that's bounded by an upper limit to this density at low frequencies from the cosmic microwave background measurements made by COBE, or maybe that's been superseded by Boomerang, the balloon experiments of the cosmic microwave background. So if you assume that in a standard model, you get this sort of limit, but if you assume some slight variations in the model, you can get a very drastic change in the slope. It's not drastic on this scale maybe, but it's drastic compared to the sensitivities of ground-based detectors. So trying to see a signal from the universe is very challenging, and it's made much more challenging by the fact that there are a lot of signals from binaries in the universe. So if you remember from the talk I gave on LISA, there are galactic binaries that carve out this section of space. This is a similar curve, but in terms of H again, this region, there's so many galactic binaries that they're unresolvable. You can't count them within the LISA time frame, whereas at higher frequencies they are countable. Okay, so that's the difference. LISA can count these galactic binaries, but not these galactic binaries. There's too many of them. If you push this sensitivity curve way down, then you'll still have all these unresolved galactic binaries. You don't really resolve them any better because you don't have enough frequency resolutions to tell one signal from another signal. So you'll have better signal sensitivity to know what the level of that noise is, but you won't be able to count them. But these will be countable. The other thing, the reason I'm showing this chart is more to show what kind of binaries there are. There are these coalescence of supermassive black holes, which LISA should see with signal-to-noise ratios of thousands. But if you improve the sensitivity a lot, you should see them everywhere in the universe. So there might be so many of those occurring at low frequencies that you won't be able to see a stochastic background from cosmic inflation compared to supermassive black hole coalescences, because it'll be just like the galactic binaries. At higher frequency in the LIGO band, you have neutron-star binaries. And where LIGO hopes to see some numbers of those, dozens maybe, if you make the sensitivity 1,000,000 times better to the point you would need to see the cosmic background noise, you would see every neutron-star binary in the whole universe, or the observable universe. And so that would give this type of background noise like this. And so we have to worry about not just stars, binary stars in our galaxy when we start talking about a mission beyond LISA that's much, much more sensitive. We have to look at all different types of binaries. So this is a new chart. This is reading material if you want to look at this. What types of binary star systems do we have in our galaxy? And with a more sensitive detector, we could see probably many, many thousands and millions of galaxies. So this is a plot from a paper by Peter Bender and Dieter Hills on different types of binaries. And CWDB is close white dwarf binaries. White dwarf binaries are stars that have burned off most of their stuff. And I'm not an astrophysicist, but there's carbon-oxygen ones, helium ones, and those stars have this type of distribution within the galaxy. And you see the numbers of them falls off at higher frequency. And what's happening is, in a crude sense, is that for a bigger type of white dwarf star, the fastest they can rotate around each other is set by the limit where their two outer photospheres interact. So they'll essentially collide and destroy themselves. So that type of mass star can't have any higher frequency than that. And so the number starts dropping off because there's proportionally fewer in that population at bigger and bigger masses. They get bigger and bigger sizes, and eventually those populations fall out. Okay, so all these different galactic binaries are going to fall out at some frequency around 10 to the minus 2 hertz. What doesn't really fall out then is the neutron-star binaries set by this curve, because they're very, very small compact objects. And black hole binaries, I don't know if anybody has any statistics for, but neutron-star binaries, there are good statistics for, or reasonable statistics for. So this curve will continue out throughout this frequency regime. So for frequencies lower than this, we're going to have all these galactic binaries and all the extragalactic binaries. But as we get into this regime, we shouldn't see stellar binaries in this frequency range somewhere, or there should be a countable number of them. And with neutron-star binaries, probably limiting the things. So this is a plot in the more traditional sensitivity regime showing LISA, LIGO 1 and LIGO 2, and hopefully that's right, and the current pulsar timing limits. So this is the sensitivity of the LISA curve, and the red area is the things that can be usefully observed, because this corner here is carved out by the uncountable galactic binaries, and the LIGO is over here. And so on this scale, these lines are lines of sort of constant energy density from gravitational waves from the universe, early universe. So it's a very steep spectrum. So at higher frequencies where you might get better sensitivity in principle, you have lower signal to look for. So you want to compromise to get the strongest signal to go as low in frequency as possible. But in order to be able to tell this background from a binary star background, you want to go as high as frequency as possible. And so Sterl has decided the best regime to look for is sort of in this regime, is a few hundredths of a hertz. So it's kind of in between LISA and LIGO. And the point is that there shouldn't be very many star systems in the universe in there. With this type of sensitivity, which is 1,000 times better than the LISA sensitivity in terms of instrumental sensitivity, you should be able to see every neutron star binary that's got that orbital period of 100 seconds or so throughout the observable universe. But you can count them. Okay, whereas if you went a little lower in frequency, there'd be so many that you couldn't count them. You couldn't see them separated in frequency. So this seems like the optimal minimum to look for. So then if you've got that kind of sensitivity, this represents the omega of 10 to the minus 15 that the standard slow roll inflation has. If you had then two detectors co-located, you could cross-correlate them to cancel the instrumental noise, and if you averaged for a year, you could look for stochastic backgrounds with this sort of signal strength. So you could get below the standard slow roll inflation limit by a factor of hundreds or 1,000.
So LIGO does just that same thing, so its actual sensitivity is considerably better than
For cross correlation, this is then going to come down to about here. Maybe.
Not quite so good. We use
Okay.
a little because the separation is not optimal. They ought to be close.
That's right.
We use some to do that. We gain quite a bit by integrating.
That's right. So I don't claim any knowledge of these curves really, except to kind of understand how to build the instrument that will do that. But still, so LIGO 2
Down 10 to the minus 8, 10 to the minus 9.
in terms of the closure density. Okay, that is assuming a specific model. It's certainly worthwhile looking at all different frequencies to see if your models are right. So you can look at broad ranges of different types of models with LISA and LIGO even, and rule out certain types of things. So it's definitely going down here in frequency. This is just the standard, simplest model you can make up for inflation. But to have some reasonable confidence with the simplest model you can calculate that you'll see something that pushes this there. And so we've come up with a configuration that would get this sort of sensitivity singly and this sort of sensitivity correlated. Okay, and it looks a lot like the LISA mission, except there's 4 of them. Okay, and the reason that there's 4 of them is for a single one, you have that sensitivity curve, but we want to cross-correlate a pair of them so that we can cancel the instrumental noise to look for a background below the instrumental noise. And so here I've shown this as a flip triangle just to show that there's 6 spacecraft there, but you actually probably would like to have the triangles actually more coplanar than that. We haven't looked into that in detail. It's a problem for the students, I think, to look at how much cancellation you get for different orientations of the spacecraft. So this gives you the cross correlation to give us the signal density that we want. But you have to look at then all these neutron star binaries in that frequency window throughout the observable universe. You have to be able to look at all their signals and map them out well enough that you can remove them as background signals so that you can look for just a pure stochastic background from the universe. So for LISA, we learn enough about the signals, we measure their frequency very quickly, but to determine their direction in the sky, LISA looks at the phase change, how can I say, it's like a pulsar timing effect. Different parts of the orbit that LISA is in, it gets a different receive time from the source, and so it can figure out the direction to the source by looking at the change in phase, receive phase over time. That's how LISA does directionality. And that's because of the frequencies LISA operates at of a millihertz or so. The lifetime of those systems is long. Okay, for supermassive black hole binaries, it's many months. And for neutron star binaries or galactic binaries, it's millions of years. So they're on for a long time. However, the sources that are going to confuse this system are neutron star binaries with orbital periods of tens of milliseconds. And those are going to radiate very rapidly and coalesce very quickly. They'll move into the LIGO, out of this band, into the LIGO band in sort of a few days. So we can't wait for this one constellation to go around the sun to determine the direction to the sources so we can map their signal well enough to remove from the background. Okay, so in order to do the directionality, we have to have 2 other detectors. So by measuring the difference in response between this one and this one, we can constrain the direction to the source along a great circle, and then between the other pair we get the other great circle.
Are they all inclined with the usual 60 degrees? This one down at the bottom looks like it's flat as a plane.
It's just hard to draw. That's actually an accurate presentation. Everything lies on a cone. They're all on the cone. The 60 degrees is magical. It makes the distance between the spacecraft more or less constant with time, which causes all the interferometer errors that you've heard about before. You do have the choice of having the cone this way or that way. And so I played a little bit with having one on the inside cone and one on the outside cone. And whether we do that here or not, nobody's tried to optimize that. It's just that the number of spacecraft needed minimum is these 12, because you need 3 for any one interferometer. If you want to cross-correlate that with the completely independent other interferometer, then you need 6. And if you need to localize all the binary star signals that are only there for a few hours or days, then you have to have 2 other interferometers, and so you're stuck with 12 spacecraft. So it's a very complex arrangement. Okay, and then, so they all look like LISA, but we want 1,000 times more sensitivity than LISA, and that it optimized at a different frequency range. So I didn't show this time, but I showed in a previous talk that if you just took the Lisa curve and you changed the distance between the spacecraft, you move this ramp where the interferometer arm is longer than the wavelength to the right, and then you move the accelerometer noise up. Okay, so optimizing here with a much larger interferometer signal means that the arm lengths are basically 100 times shorter than the Lisa arms. Okay, so to get 1,000 times better, we're going to do 100 times shorter arm length with 1,000 times better intrinsic sensitivity. I don't know if you remember, the Lisa sensitivity, the bottom sensitivity, its best sensitivity in terms of H, is independent of separation. You can change the frequency regime over which it's operated, but the shock noise, the received power, goes up as you shorten the arm, but you divide by an arm length that's shorter, and so that actually cancels out. So to get 1,000 times better sensitivity on this 100 times shorter arm length, you need to have a lot more laser power coming in from the other end, 1,000 times, well, 1,000,000 times more power. Okay, and I did reproduce this here. Let me go forward. The shot noise goes like this formula. The length, the diameter of the transmitting mirror seems like the easiest parameter to play with. The laser power is the other one, this piece of L. The laser wavelength, we're not sure we can ever come up with a laser wavelength that's effectively better than the 1,064 microns or 1,064 nanometers for the neodymium YAG laser. So we think about going to a 3-meter mirror, which is a Hubble telescope class mirror, and a 30 watt or 100 watt laser. So there are 100 watt lasers now. LIGO is using sort of 30 watt class lasers. There are kilowatt class lasers under development. The problem with the kilowatt laser is they're about 10% efficient in terms of electrical power versus laser power. So if you want a kilowatt of laser power, you need 10 kilowatts of solar power collection. So it's a huge solar array. So it seems like a better trade to optimize the mirror size and just pick a reasonably large laser. It goes like the square root of the power anyway.
Are those larger lasers, have they been space qualified at all?
No, right now it's not clear any lasers have been space qualified.
However, when do you imagine this launches VBO?
Nobody's talked about a realistic launch date. It's beyond 2020. This is a long, long time away. Lisa's going to launch.
About a few years to space qualify.
That's right. The thing is, the lasers work on the ground at 100 watts. Okay, and space qualification mostly involves radiation and then making them rugged enough so that when you shake them on the rocket launch that they don't fall apart. So that's pretty straightforward, it's just application of a certain amount of money. But coming up with, say, a 100 watt laser at a shorter laser wavelength is much harder, right? Because now you need a different type of crystal material that's got a resonance that's appropriate, that's stable enough, and a narrow enough line width. And that's hard. And so that hasn't really changed in the last 10 years, what laser wavelength we're talking about using. People have talked about frequency doubling, so using the same intrinsic line but then doubling the frequency. The problem is that power conversion inefficiency is much worse than the square root of the power that you gain right now. So that might gain you something in the long run, but right now that doesn't look good. Okay, but another 10 years, who knows? We've been talking about flying ultra-stable oscillators, right? We need a frequency standard of this 10 to the minus 16. The space-qualified oscillators have improved from 10 to the minus 13 to 5 times 10 to the minus 14 in the last 15 years. All right, so progress in that field has been very slow. So I don't think you want to count on it. Whereas a 3-meter mirror has flown, okay, and they've gotten much cheaper to manufacture on the ground. But 12 of them, it's a big launch vehicle problem to do that. Okay, so we go to 3-meter mirror, 100 times shorter baseline, and then Lisa's really pushing on the acceleration noise on the test mass. And we said, well, Lisa's pushing a factor of 1,000,000 above the current state of the art. And we said for this that, well, maybe another factor of 10 would be sufficient. Oops. Okay, and a factor of 10 pushes this curve up and down a bit. So it would cut into this minimum, but not by a factor of 10. So if we were limited in Lisa performance only, we wouldn't lose a factor of 10 in performance here. Also, the performance that we're really most interested in here is high frequency compared to LISA. So most of the noise sources we expect on LISA to accept the test mass are worse at low frequencies in here. So probably getting a 10 times better performance than the LISA performance at this frequency range won't be so outstanding a problem. We probably could do better than that. But we're not trying to stretch it for LISA and then to here. So here we've just stretched the interferometer noise budget. If we could do this better, we would get more room here, and maybe we could re-optimize. But this seems like a good starting
So
point.
did you say what those curves are that you just drew on before class?
This course, this in omega in terms of closure density, this is 10 to the minus 15, I think.
Oh, that was 10 to the minus.
And this is 10 to the minus 10. Okay, so 10 to the minus 10, LISA has a shot of looking at. But we don't expect that from our standard model for slow roll inflation. 10 to the minus 15 is sort of the upper limit from standard slow roll inflation. So LISA should be well above that limit. LIGO should be well above that limit. We want to push down.
With VBO correlated, it looks like you go down to 10 to the minus 18. Your dashed curve for VBO correlated.
Yes, it might go to 10 to the minus 18. And because different models have these steeper slopes, you might have to go that far. So this is just about as far as we've come thinking about this idea, trying to pick a regime to work at, trying to calculate what the background signals are, trying to figure out the minimum detector sensitivity that needs to be done to get there. Okay, but there's an awful lot of thinking that could be done on this if somebody wants to write a summer paper or a senior thesis or something. There's a lot of problems in terms of removing the signals. This is something of interest for LISA, in fact. If you know there are 1,000 binary signals and you know what they all are, how well do you have to know them to remove them in order to look for stochastic background? Okay, that's not a trivial problem. Looking at the directionality of the sources, how well do you have to measure the directions with the triangularity of the spacecraft as they move around? How much do you have to have the interferometers co-located to get the cancellation that we need to get this big factor jump for co-location? There's lots and lots of interesting problems here. In terms of the instrument problems, I wouldn't go and build any of this stuff yet. But getting a 3-meter mirror, that's not so challenging, but there's this antenna pattern noise, the pointing noise that corresponds to having this 100 times shorter and 1,000 times more sensitivity, means that we need a lambda over 200 mirror, and the Hubble telescope isn't that good. It's about lambda over 50, so that's a manufacturing problem. And then we have to point with 50 picoradian accuracy. That's pretty daunting. If we're going to measure 1,000 times better for LISA on the shorter arm length, LISA's measuring 10 to the minus 11 meters per root hertz, which is 1,000,000 times worse than LIGO. Doesn't seem like it's so hard. It's a low frequency. There's some low frequency noise to worry about. 100 times shorter arm, 1,000 times better sensitivity is 10 to the minus 16 meters per root hertz. All right, that's creeping up on where LIGO is. All right, if 10 to the minus 16 divided by a kilometer would be 10 to the minus 19 in H, and LIGO's what, 10 to the minus 21 maybe. So that's pretty close. So trying to do that with a non-equal arm interferometer, nearly as good as you're doing an equal arm interferometer today, that's very challenging. So an interesting little project would be to see what would be the effect of actually steering the spacecraft. Remember, it's 100 times less than LISA. So the steering problems to keep the arms exactly equal would be 100 times easier than for LISA. So the effect on the test mass noise of pushing the masses around the little bit that you need to keep them there, so you can have an equal arm interferometer, that might be an interesting problem to look at. It's a possible trade. Otherwise, you have to do this very, very accurate phase measurement on 2 different arms and cancel them. Very, very challenging. Okay. We also have this Doppler shift noise, but that turns out to be about a wash. 10 to the minus 16 is what you need for LISA. That's what you need for this. It's just because the Doppler shifts are smaller. So that turns out to be not the biggest problem. But this pointing problem and the measurement noise, those are challenging. So there's lots of work to do on that in the future. So there's some theoretical work down that could be done now. Some papers could be written for conferences and things. I think nothing is written on this. So there's a big area, but there's some interesting little problems. Okay, so that's all I was going to say.
Thank you, Bill. Any questions?
So these are just some equations.
Thanks.